Chapter 2 starts by answering the question for us, how do we know that everything is made of atoms? Well, in sections 1 and 2, make sure you have your notebook, pencil, and a periodic table out, and take these notes down. And we'll start to answer that question by looking way back to 400 BCE. Well, at that time, the Greeks had a word for indivisible particles that made up everything, and that word was atomos. And from there came the first ideas that everything was made up of small indivisible particles. That went dormant for a number of years, and then in about 1790 or so, a gentleman named John Dalton came along, and he had the first atomic or atom theory. He had 4 postulates, or 4 pieces, that he based his theory upon. First of all, was that each element that they knew of at that time was composed of really small particles called atoms. Secondly, that atoms of oxygen were always the same, but they were different than atoms of something else, like nitrogen, for example. Thirdly, he said that you can't change one into the other. You can't change lead into gold, which, of course, was a belief for many years, but you cannot do that. And then fourthly, you can combine 2 or more of these atoms into something called a compound. And nitrogen and oxygen atoms could become nitrogen and oxygen. And so this was the first time that beliefs carried through for many, many years, and the theory grew. The theory grew and was built upon for many years after that. In about 1850, or around that area, and before that even too, there were these things, there was a little belief or a knowledge of electricity actually well before this. When they'd take 2 dissimilar metals and put them into solutions, they could get like a charge, or they'd feel some type of current. And they started to be able to have this discharge tube called a cathode ray tube in the mid-1850s, mid-1800s or so. And this is what one of the first ones kind of looked like. They took this tube and they pumped it out of air, or as much as they could back then. And then they would take an electric current and run it from one end through the other. They didn't really know it was called that at that time, but what they discovered was that when they did this, if they put a phosphorescent or glowable type material around the tube, they could see this ray, and they called it a cathode ray, and that was the first words for it. Anyway, what was interesting to them was that if they took a magnet and brought it near this cathode ray, it would bend the ray. You can see it's actually bent a little bit this direction. And if you brought the positive end of the magnet, then the ray would bend towards the positive end. If you brought the negative end towards it, it would move away. And J.J. Thomson was the famous scientist at that time that was first discovering this, and he said, so maybe the things that make up these rays are actually parts of these things called atoms, and since you brought a positive end of a magnet near it, maybe the ray or the beam that went through was negative in charge. Here's a more modern view of one. And you can see that they actually can take little charged plates across this cathode ray right here, and then they can cause it to bend in different directions and actually make like a fluorescent screen, or maybe make something that looks like movement. Some of the first ways that they started to make moving pictures, other than just like flipping them through a book or lots of pictures up on a screen, were with these types of rays. Along came another gentleman named Robert Millikan, and these ideas that everything was made of small particles, and these small particles called atoms might even be made up of other things, intrigued people, and he wanted to find out what this negatively charged thing was. And so he did what was called the oil drop experiment, and he took drops of oil and then dropped them through this field of electricity. You can see the plus and the minus right here. Scanned them with a source of X-rays, which he sort of knew what they were at that time. And through that, he determined the charge to mass ratio of this negative particle. From this, he was able to derive that there was a mass to this negatively charged thing that he called an electron. And this tiny, tiny mass times 10 to the negative 28th grams was actually fairly close to what we know it is today. At the same time that this was going on, a couple of other famous scientists in the late 1800s started working with these things called radioactivity. And you've probably heard of Marie Curie and her husband, worked with Henry Becquerel, and they were Nobel Prize winners in the area of radioactivity. Well, radioactivity also helped us study what were these atoms, or these things that made up everything else. Well, first of all, what is radioactivity? Well, radioactivity is some substance that spontaneously or by itself would emit something of energy. And uranium was the thing that the Curies studied, and they classified 3 different kinds of radiation or radiant particles or pieces that this radioactive source would emit. One is called an alpha particle. An alpha particle is a positively charged particle right here, and you can see that here is a radioactive substance like uranium, and then what they did was they took electrically charged plates, and then when they had positive and negative electricity going through there, or electrons moving through the wire, which they didn't really know for sure, but they knew that one was positive, one was negative. They noticed that these alpha rays were pulled towards the negative side, which were composed of 2 protons and 2 neutrons. And even though we haven't talked about it yet, you know that protons are positive, and that's what made it be pulled towards the negative part. The second type of radioactivity was beta radiation, and these were pulled towards the positive part of the plate. And if you look real close at the book, you can see that they're actually deflected more towards the positive part than the alpha particles were deflected towards the negative part. That's because these are lighter. They're made of electrons, not protons and neutrons, and they are negative in charge, so they were pulled towards the positive plate. And then there was a third type called gamma radiation. These are high-energy photons that carry no charge. They don't have a positive or negative charge as well, and these are the ones that are probably the most dangerous to humans, and unfortunately were dangerous to the people that were studying them at the same time. They used these X-rays. There are these types of alpha particles, beta particles, or gamma particles. Gammas are usually near the X-ray areas, as probes to explore the tiny thing they called the atom and find out what is this atom, indivisible particle, actually made of. In the early 1900s, there was a model of the atom. It was called the plum pudding model. J.J. Thomson had this model, and he said that there were positive and negative particles mixed in this spherical shape, and they were just randomly mixed throughout. Well, they weren't sure about this, and so along in 1910 came a landmark experiment named the gold foil experiment by Ernst Rutherford. Here's a picture, an interpretation kind of what it actually did. He had a source of alpha particles, and if you remember, alpha particles were positive, so I put a little positive, 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 like a beam of particles right here coming out of a source of alpha radiation. And then he took this super, super thin sheet of gold, kind of like aluminum foil, but even thinner than that. And then he said, well, all of these big, heavy, positive particles right here should pretty much go straight through this gold foil because it's so thin and these particles are so small that they'll just like zip right through and it won't hit the atoms. And many of them did. They shot straight ahead and they recognized, oh yeah, there's lots of these alpha particles that are noticed as going straight through the gold foil. But what was interesting was that some of them were deflected straight to the side. A very few were even deflected straight back. And since the alpha particles were positive in charge and should have been heavy enough to just go through, if they were deflected backwards, that means inside this gold foil there must be some dense positive charge inside of there. And lo and behold, that dense positive charge turned out to be the nucleus inside of the atoms of gold. And the few of the alpha particles didn't make it through, but bounced off of those nuclei. And hence, as we'll see in the next video, we came up with this nucleus and electrons on the outside modern view of the atom. Next video.